Corner-grounded delta system is an electrical power system configuration where the neutral point of the delta-connected transformer is grounded through a resistor or impedance. This system aims to provide a low impedance path for fault currents, which can simplify fault protection. However, corner-grounded delta systems are generally not considered as safe as other grounding systems like solidly grounded or resistance-grounded systems. There are several safety concerns associated with corner-grounded delta systems. Firstly, high fault currents. During a phase-to-ground fault, the fault current can be very high because of the low impedance path. This high current can lead to equipment damage, arcing, and potential fire hazards. Secondly, overvoltages. Ground faults in corner-grounded delta systems can cause overvoltages in the healthy phases. These overvoltages can damage equipment and disrupt operations. Thirdly, lack of single-phase fault protection. Corner-grounded delta systems do not inherently provide protection against single-phase faults. Fault current in these situations may be too low to trip the standard overcurrent protection devices. Fourthly, high step and touch potentials. During a ground fault, the voltage in the grounded phase can increase significantly, creating high step and touch potentials around the faulted equipment. These potentials can pose a significant electric shock hazard. Despite these safety concerns, corner-grounded delta systems are sometimes used because they offer a few advantages. Firstly, reduced harmonic distortion. Corner-grounded delta systems tend to have lower harmonic distortion compared to other grounding systems. This can be beneficial in sensitive electronic equipment. Secondly, lower equipment costs. The grounding resistor or impedance required for a corner-grounded delta system is typically less expensive than the equipment needed for other grounding methods. Thirdly, improved power quality. Corner-grounded delta systems can help maintain a more stable voltage during normal operating conditions. If a company is considering installing a corner-grounded delta system, a careful evaluation of the safety risks is crucial. Several precautions should be taken to mitigate potential hazards. Firstly, install high-quality fault protection devices. Overcurrent and ground fault relays should be specifically rated for the high fault currents that can occur in corner-grounded delta systems. Secondly, provide adequate grounding. The grounding resistor or impedance should be appropriately sized to limit fault currents and overvoltages. Proper grounding is essential for safety. Thirdly, implement grounding monitors. Alarms or indicators should be installed to continuously monitor the grounding system. These monitors can alert operators to any potential problems, allowing for prompt corrective action. Fourthly, train personnel. All personnel working in areas with corner-grounded delta systems should receive thorough training on the associated safety risks and emergency procedures. Understanding the system's characteristics is vital for safe operation. If possible, it's generally preferable to use a solidly grounded or resistance-grounded system instead of a corner-grounded delta system for improved safety. These alternative systems offer better protection against various fault conditions. In summary, while corner-grounded delta systems have certain advantages, their safety concerns necessitate careful evaluation, robust protection measures, and thorough training. Always prioritize safety when choosing and implementing electrical grounding systems. Grounding systems in electrical engineering are designed to protect people and equipment from electrical faults. Different grounding methods each have unique characteristics and applications. A solidly grounded system is one where the neutral point of a transformer or generator is directly connected to the earth. This provides a low impedance path for fault currents, allowing for quick detection and clearing of ground faults. The primary advantage of solidly grounded systems is their ability to limit voltage rise during ground faults, preventing damage to equipment and reducing the risk of electric shock. However, the high fault currents can cause significant equipment stress and require appropriately rated circuit breakers and conductors. Resistance-grounded systems introduce a resistor between the neutral point and ground. This resistor limits the magnitude of ground fault currents, reducing stress on equipment and minimizing voltage dips during faults. There are two types of resistance grounding: low resistance grounding and high resistance grounding. Low resistance grounding typically limits fault currents to a few hundred amps, providing a balance between fault current limitation and ease of fault detection. High resistance grounding, on the other hand, limits fault currents to very low levels, often less than 10 amps. This significantly reduces the risk of arc flash and equipment damage but can make fault detection more challenging. Ungrounded systems, also known as isolated systems, do not have a direct connection between the neutral point and ground. While this might seem counterintuitive, ungrounded systems can continue to operate during a single ground fault. The first fault creates a floating neutral and no significant fault current flows. However, the voltage to ground on the unfaulted phases increases, and a second ground fault on a different phase will result in a phase-to-phase fault, which can be severe. Ungrounded systems are typically used in applications where uninterrupted operation is critical, such as in some industrial processes. A corner-grounded delta system is a type of grounding arrangement used with delta-connected power systems. In this configuration, one of the phase conductors is intentionally grounded. This creates a grounded system but with different characteristics compared to solidly or resistance-grounded Y systems. One of the main concerns with corner-grounded delta systems is the potential for high fault currents during a ground fault. Because one of the phase conductors is directly grounded, a fault on that phase results in a very low impedance path, leading to high fault currents. These high currents can cause equipment damage and pose safety hazards. Furthermore, corner-grounded delta systems can exhibit overvoltages on the ungrounded phases during ground faults. The voltage on these phases can rise to levels significantly above normal, potentially damaging equipment connected to those phases. Corner-grounded delta systems may also lack adequate single-phase fault protection. The fault current during a single-phase fault might be too low to trip standard overcurrent protection devices, leaving the fault undetected and potentially leading to further damage. Step and touch potentials are also a concern with corner-grounded delta systems. During a ground fault, the voltage on the grounded phase can increase substantially, creating dangerous voltage gradients around the faulted equipment. This can pose a significant electric shock hazard to personnel in the vicinity. Despite these concerns, corner-grounded delta systems are sometimes used in specific applications. They can offer some advantages, such as reduced harmonic distortion compared to other grounding systems. The grounding impedance required for a corner-grounded delta system is typically less expensive than the equipment needed for other grounding methods. Corner-grounded delta systems can also help maintain a more stable voltage during normal operating conditions. However, the safety risks associated with corner-grounded delta systems must be carefully considered and mitigated. If a corner-grounded delta system is being considered, several precautions should be taken. High-quality fault protection devices such as overcurrent and ground fault relays should be installed. These devices should be specifically rated for the high fault currents that can occur in corner-grounded delta systems. Proper grounding is essential for safety. The grounding impedance should be appropriately sized to limit fault currents and overvoltages. Continuous monitoring of the grounding system is crucial. Alarms or indicators should be installed to alert operators to any potential problems. Comprehensive training should be provided to all personnel working in areas with corner-grounded delta systems. They need to understand the associated safety risks and emergency procedures. Whenever possible, it is preferable to use a solidly grounded or resistance-grounded system instead of a corner-grounded delta system. These alternative systems offer better protection against various fault conditions and improve overall safety. The choice of grounding system depends on various factors, including the specific application, the sensitivity of equipment, and a desired level of safety. A thorough analysis should be conducted to determine the most appropriate grounding method for a given situation. Each grounding system has its pros and cons. Solidly grounded systems provide excellent voltage stability but can result in high fault currents. Resistance-grounded systems limit fault currents but may require more sophisticated fault detection methods. Ungrounded systems offer uninterrupted operation but can lead to overvoltages and require careful monitoring. Corner-grounded delta systems have specific advantages in certain applications but pose significant safety risks if not properly implemented and maintained. Electrical codes and standards provide detailed guidelines for the design and installation of grounding systems. These codes specify requirements for conductor sizing, bonding, and grounding electrode systems. Compliance with these codes is essential for ensuring the safety and reliability of electrical systems. Regular inspection and testing of grounding systems are necessary to verify their effectiveness. Ground resistance measurements should be taken to ensure that the grounding impedance is within acceptable limits. Ground fault protection devices should be tested to verify their proper operation. Proper grounding is a fundamental aspect of electrical safety. It protects people and equipment from electrical hazards and ensures the reliable operation of electrical systems. Understanding the different grounding methods and their characteristics is essential for electrical engineers and technicians. By carefully considering the specific application and implementing appropriate grounding techniques, it is possible to minimize the risks associated with electrical faults and create a safe electrical environment. The NEC, or National Electrical Code, provides comprehensive guidelines for electrical installations, including grounding and bonding requirements. Article 250 of the NEC covers grounding and bonding, providing detailed rules for ensuring electrical safety. The NEC specifies the types of grounding systems that are permitted, the methods for grounding different types of equipment, and the requirements for grounding electrodes. The code also addresses bonding, which is the connection of metallic parts to create a low impedance path for fault currents. Proper bonding is essential for minimizing voltage differences and preventing electric shock hazards. The NEC includes specific requirements for grounding different types of equipment, such as transformers, generators, motors, and electrical panels. These requirements vary depending on the voltage level, the type of system, and the location of the equipment. The code also addresses grounding electrodes, which are used to connect the grounding system to the earth. Acceptable grounding electrodes include metal underground water pipes, metal frames of buildings, and ground rods. The NEC specifies the size and installation requirements for grounding electrodes to ensure that they provide a low impedance path to ground. In addition to Article 250, other articles of the NEC also address grounding and bonding requirements. For example, Article 500 covers hazardous locations, which require special grounding and bonding methods to prevent explosions and fires. Article 517 covers healthcare facilities, which have stringent grounding requirements to protect patients and medical equipment. Compliance with the NEC is essential for ensuring the safety and reliability of electrical installations. Electrical inspectors use the NEC as a basis for evaluating electrical systems and ensuring that they meet minimum safety standards. Failure to comply with the NEC can result in fines, project delays, and increased liability. Grounding and bonding are critical aspects of electrical safety. By following the guidelines in the NEC and other relevant standards, it is possible to minimize the risks associated with electrical faults and create a safe electrical environment. The proper design, installation, and maintenance of grounding systems are essential for protecting people and equipment from electrical hazards.